Hello, everyone. So today we'll present you our project, which is internet traffic optimization using reinforcement learning. So we'll start with the motive of the project and talk about how we approached it and present the results. So let's first talk about the current state of the internet. So the internet has revolutionized our life. It has basically shaped what we do over the last 20 years. It's a very important aspect in our lives. And clearly there's as you can see, there's a direct correlation between developed countries and internet use. But traffic is increasing at an exponential rate, which is not surprising, but it's putting a strain on the network and increasing congestion. Although the speed is increasing, because how we approach the problem until now is by just adding capacity. So physically improving our networks more and more. However, with the exponential increase of traffic and also with the change in format of what is being sent on the internet. So when we used to do text and images, now we're sending high definition content, 4K. So it's increasing in size and volume, and the format is also putting a strain on it. So keeping up with the same solution, which is adding more and more capacity, is going to be exponentially costly because traffic is also going to increase exponentially. And it's unable to keep up with the actual increase in traffic. There's actually a physical limit to how much you can actually put and in terms of links. So we need to think about how to solve this in a different way. I'm not saying we should drop the solution of increasing capacity, but we should combine it with a different one to make the internet more efficient. And so we need basically a smarter network to work along with the evolution of the physical network. So what is the internet? The internet is basically a connection of subnetworks. We, the end users, send stuff. We are connected to a local area network, and the messages travels up, and from the local internet service providers to the regional one, all up to the internet's backbone, which is consisted of a wide area network, which connects. Basically, this is where we share the resources with everybody who uses the internet. It is then routed to the correct exit, which is connected to the local area network of the receiver, and then it travels down up until it reaches the receiver. So we could make an analogy of the internet with actually regular traffic. So the cities are actually connected by highways, and inside the cities you have small streets. So whenever you want to travel to a different city, you actually need to take the exit that's actually closer to the next city and route, and so take the steps which will get you closer to the next city. How it works with the internet is basically, so you send a message, the message gets segmented into packets, and then each packet is sent and reassembled at the destination. So whenever there's high traffic, there's high congestion, there's a higher latency to the message, so reliability is decreased. What you can do with regular traffic whenever there's high congestion is basically take a detour and take a road that is less congested. But this might not be very efficient. It might not be a good choice because you would actually have to travel longer physically and put more time, and when you could have sat in traffic and waiting. But with internet and packets, because they're electrical signals, it might be very logical to actually send it far away and route it through a different way back to the destination and avoid having this passing through the congested traffic. And so doing so will enable us to actually reduce congestion points, distribute the traffic all around the network, and so basically make use of the distributed computing system that is the internet to actually have a more reliable, more efficient service. And it actually doesn't cost that much because basically it's just software. So we'll have just change software instead of building stuff and having an increase in cost. And so what can we do to route the packets differently? And what we try to do basically is apply reinforcement learning. So so I have an agent look at a network and decide how traffic should be routed, for every hop until it reaches its destination. So for doing reinforcement learning, we needed the fourth stuff, which was the environment, a traffic generation, an agent, and a neural network. So for the environment, before deciding how to build it, we first have to ask ourselves, what kind of network do we want to simulate? And so is it a local area network? Is it a wide area network? What kind of communication links are we using? Are we using a one-way communication link or a two-way communication link? There's actually also different topologies, mesh, three-ring, and star. And so in order to make our decision, we actually research where congestion is mostly a problem. And it's definitely where we share the most resources, which is a wide area network. A wide area network consists of a mesh, kind of a mesh topology. And it has a two-way communication link. So a router can send at the same time as it is receiving. And so yeah, basically, and with that, we started building our environment. Okay, so this is the network that we use. It's basically made out of 5 nodes. You can visualize the nodes as being cities and the actual links as being like the highways connecting the cities. Each node has a queue size where the messages are actually queued until they are processed and routed to the next destination. And apart from that, we have different actions available based on how many links you've connected to. So basically, node 1 is connected to 2 links. It has 2 actions, and there's also the action with 0, which is do nothing. And so whenever a packet is routed, if it reaches the destination, it actually disappears from the environment because then it travels down. So basically, if we wanted to go to Berlin and we reach Berlin, then we go inside Berlin and go to wherever we want there. So we're not in the network of highways. And we get basically a positive reward because we reach our destination. Whenever it is routed somewhere else, well, depending on the queue occupancy, because we want to actually favor less congested queues, we assign a negative reward, which is the minus, so the next queue occupancy. And finally, the reward of -0 is assigned whenever we're taking an action 0 and there's still packets that needs to be sent and queued. So basically, our environment looks kind of like this, which is a multi-discrete action. So you're taking 5 actions every time. Each action there's 4 options per actions, 3 for node 1 because it has 2 connections, and our state is modelized by a 2D network with a 5 by 10. 10 because we decided to have a queue size of 10, and 5 because we have 5 queues. So to make it better visually, we first have to talk about traffic generator first. So the traffic generator, we have 5 waiting queues for each node. So each node for each node, there's a incoming traffic. And so these are called waiting queues basically, and they have different rates. So these rates basically define how busy the traffic is in this node. And we could simulate a stable traffic with every node having the same range, having the same rate, or we could actually congest a region or congest a specific node and observe how our model changes. So whenever the incoming traffic arrives, if there is space, the packet is actually added to the bottom. Because it's like this is how it should be. Whenever it is routed, it's added to the top because we want to prioritize the delivery of the earlier packets, so not having them run through our network endlessly. And whenever there's no size in the queue, we have a dropped packet, and so we have this metric that basically gives us an information of how reliable the network is. So putting it all together, to make it visually understandable, let's say that you have 5 nodes, 5 colors. The roads are actually the access to the nodes, and so basically the traffic generator makes use of the roads, and the roads are also used to route the packets to the lands whenever they are delivered to the right node and back. So in here we have on the left the current state, which consists of the queued cars, which have the colors based on their destination. So the action we're taking an action. and then we have a new state. So the blue car on the bottom is queued in the queue of the yellow one to indicate that basically there's incoming traffic. Because as we can see, we're taking 2 red actions, and these actions are for node 5 and 2. And so they have at the top red cars. So 2 red cars are routed to the correct location, and they leave basically the environment. And apart from that, basically, this is how the routing works. And it's basically, this is just a theoretical explanation. What is actually happening is there's like lots of more movements of packets and cars and whatever. So Naveen is going to talk now about the agent.
Yeah, thanks, Karim, and hi everybody. So I'll be looking at agent part and a deep neural network part. So here I'll be explaining why we have selected this kind our agent and why we have selected our neural network. So before that, I'll be bit of about reinforcement learning algorithm. So and it can be divided into 2 types. One is a model based and one is like a model free. And in model based, it determines its own path. So we give basically first like a path and it takes the directly actions. In model free, it is other way around. And under model free, we have 2 types. One is a policy optimization and one is another is like a Q learning. And in model based, we have like a learn the model and a given the model. Yeah. So in our case, we have selected actor critic algorithm by doing a lot of research. And in our case, we have like we have 5 actions, and each action has like 4 steps. And here in actor critic method, what exactly actor does? So actor is like it creates its own policy, and by taking critic reviews. So critic gives the value and it gives the feedback to the actor, and then actor takes this action, and action goes to the environment. Then environment will give back to reward and new state. From there, we can calculate advantage function. So once we get advantage function, by using advantage function, we can calculate gradient. So we take these values to feed our neural network. In our case, we have selected convolutional neural network, and it's very good in so it's very good in giving extracting features. So in our case, we have 3D space. So it takes the 3D space and gives to convolution layer. Then it goes to the pooling layer, and then does flat. So from flattening so it goes to a fully connected layer, and we get our results. So in our case, we use 2 convolution layers and 2 fully connected layers. And so once we feed this before feeding this, we have to do a bit of pre-processing. So in our case, we have 2D space. So we have to convert 2D space to 3D space. So how we did this one? By using one hot encoding. So once we got this 3D space and we fed this value to our network, and we got our output. So we got total 10 outputs. In these 10 outputs, we have 5 actors, and we can see here in picture, in 5 actors, we have total 4 steps, and we also got 5 credit. So this is how we got our results. And next, Karim will be handling about results and conclusion parts.
Basically, our agent was the actor critic, because basically we did not have a policy. We don't know what strategy to use. So we wanted our model to come up with its own strategy. So we wanted to have some kind of policy optimization algorithm. But on top of that, we also, because we have a huge action space with like 5 actions and 4 possibilities for each action, which is basically why our actor layer looks like this. It will be very inefficient of just having a simple policy optimization. And plus, we really needed to have some more information about the state, whether it's congested or not. So basically the critic, which evaluates which is also a part of the network, it evaluates the state. So combining both, we're able to train it better. And this is why basically the actor critic works well technically. So as for training results, we first trained our first model, and it was basically with a different routing penalty. So we were assigning -5 instead of the next queue occupancy. And what we found out is that basically after running multiple episodes, it stuck to one loop. So basically the red one, and so it's constant action, which lets all packets travel around the network. So basically everything will be delivered at one point, but obviously it's not the optimal path. And whenever because basically this training we did not have the traffic generator in it. So it was the first one. So whenever we will add the traffic generator, things won't work as well with this, and we will have dropped packets. And and as you can see, that like the variance basically stops changing for the score at the end, because it sticks to this move, and this move basically yields like the same results technically. So our second model, which is including the next queue occupancy as a penalty, and doing that enabled us to basically get better results. So in here, we're looking at average of the average running scores, basically to be able to figure out the trend, because it was very like the variance is very high whenever the training is happening. On the left, we have a random baseline, which technically sticks around between like the less than -1,000 as a score. But on the right, we can clearly see that our agent is becoming better, and like over time, and we're training it with 3,000 episodes, which is not much, but like using the computing resources that we have, it took like 3 hours at least. And apart from the score, we also measured the runtime, which means in how many steps an episode is completed. And the same thing is happening over here. So the runtime is increasing, which means that our agents are becoming smarter, taking better moves, and basically ending the episode faster. And because we don't have a traffic generator, we're just ending the episode whenever all the queues are empty. So there's actually great promise in implementing reinforcement learning to a network. As we can see, it's improved, like it learned a lot, and it's basically with like very little resources. So with more and more training, things can be better. And the next steps would be to plugging in the traffic generator, which is very important for us to simulate real life events. And that's for actually deployability. Additionally, it could help us test for latency and dropped packets, as whenever packets cannot be queued into the nodes, they will be dropped. So it will help. We will have like this metric, which will indicate information on the reliability of our network, and the order of delivery of the packets, which can put a strain on the receiver. That also can be measured. We will also need to increase our queue size and network to simulate a real wide area network. And what we can do actually is use the core emulator, which is basically an emulator, like it differs from a simulation, being that it actually collects the real data from the real networks, and we could use these to see how our network will perform on real world data without having to worry about having a simulation that fits 100% real life events. And